Good morning to one and all present over here. I am Cadet Rohan. So today we are going to learn circular motion. So circular motion is divided into two parts. One is kinematics and another is dynamics. So we have to learn kinematics first so that we can understand the dynamics part, because kinematics clears basic concepts like tangential acceleration, normal acceleration and many other things. So let us start with our today's first concept, that is tangential acceleration. So let us denote this by AT. So first let us imagine a case where there is a random path like this. At this point the velocity is like this, in this direction, and let us consider the acceleration, the net acceleration here, and the angle made by the acceleration and the velocity is theta. So we can understand, or we know that this net acceleration makes two component, that is one component it is a cos theta and the other component is a sin theta. So what we'll do now, this acceleration is broken into two further components. So we can see that as this a cos theta is parallel to the velocity and has the same direction of velocity, and it is a tangent of this point. So we name this as tangential acceleration, which is equal to a cos theta. And as this is normal, this makes a normal with the velocity, or we can say it is a perpendicular to velocity. So we can say that this is normal acceleration, which is denoted by an, or we can also say that this is also known as centripetal acceleration, which we'll learn in the dynamics part. So what we can understand from the tangential acceleration is that first the magnitude of tangential acceleration is a cos theta. So as we are saying that it is a cos theta, so if we try that to represent it by vector form, so we can write it, it is the dot product of net acceleration and velocity acceleration. So what we want to derive, a cos theta, but we know that this value is equal to AV cos theta. So we need to eliminate this V from here, right, to get this a cos theta. So what we can do is we will write this by the magnitude of V, which will give us a cos theta. So we can say that the dot product of acceleration net and velocity divided by the magnitude of velocity gives us a cos theta, which is equal to tangential acceleration. So now let us understand what is the function of this tangential acceleration. This tangential acceleration gives the changes the magnitude of velocity or speed, as we are seeing that in this case acceleration tangential is parallel to the velocity. So we can imagine this situation by this observation, that if it is a duster and it is moving with certain velocity and I am pushing it further in the direction of velocity, so what will happen? The speed will increase. We know that whenever there is a force, there is an acceleration, because force is equal to mass into acceleration, that we have learned in Newton's law of motion, that comes from second law of motion. So in this case there is an acceleration and there is a velocity. So what is the cause of this acceleration? This is so there must be a force which is acting upon it, which we will call as centrifugal force in our subsequent classes. So for right now we can say whenever this is parallel to velocity, the speed increases, and if it is anti-parallel or opposite direction, they are in opposite direction, anti-parallel, then then the speed will decrease. Okay, so basically tangential acceleration is tangential acceleration is there to change the magnitude of velocity, which is change speed. Okay, so now we can also write, therefore, so we can define how we can define tangential acceleration. We can define tangential acceleration, we can say that it is the rate of change of speed with respect to time. Okay, or we can simply say it is the rate of change of speed. So if we want to write this equation mathematically, we can say that differentiation of speed with respect to time gives us tangential acceleration. And also if we want to try it vector wise, we can write that at plus an means this is the centripetal acceleration, is equal to a net. Vector wise if we write, so we can say that at is equal to a net minus a. So this is an important formula which we can remember, right? And now the last thing is, if we consider a case where at is equal to 0, so what will happen to the motion? So if tangential acceleration is 0, the magnitude of velocity, that is speed, will be constant. Why it will be constant? Because we know that the tangential acceleration changes the magnitude of speed, but if it is 0, then the whole speed is constant. Like this, if an object is of mass m is moving with a velocity of v, can you see the magnitude is not changing? At t is equal to 1, it is moving with velocity v, and after some time, if let's consider t is equal to 4, it is also moving with same velocity. So at this case the acceleration is equal to 0. So I think that we got an idea of this tangential acceleration. Now let us focus on what is normal acceleration. What is normal acceleration? So again, for normal acceleration, we will again make that same diagram like this. Now what is normal acceleration? This is the velocity, this is the direction for velocity. Okay, this is, let's say, acceleration net, and so if the angle is theta, then this will be tangential acceleration and this will be normal acceleration, which is equal to a sine theta. Okay, so now what we want, actually, we are saying that the tangential acceleration is changing the magnitude of velocity, and this is giving the direction. Can you see that this is giving the direction? How it is giving the direction? Like we say, in a projectile motion, the motion is like this. Okay, so it has a certain velocity like this, and it has a certain angle theta. So this becomes v cos theta, and this becomes v sine theta. So this velocity provokes the object to move upward, which helps to reach this height, and this velocity helps to move make a range to move in the direction of x-axis, in the direction of x-axis, right? In the direction of x-axis. So we also represent it like this. If we want to represent it vector wise, so we can represent it I cap and we can write it j cap. Okay, because it is having direction this way. So similarly, this acceleration, which is known as normal acceleration, helps us to give the direction of the object, of any object. It helps us to give the direction, okay, and it changes the magnitude. So what we can first, let us say what is that normal acceleration value. It is equal to a sine theta. Okay. So again, so this is a sine theta, right? Now if we want to again write it vector wise, we can say it that at vector wise plus an vector wise is equal to a net, right? So from here we can say that an is basically a net minus a t. Okay, this is important. Now if we want to write it another way, so we can also say that this is the acceleration, and if we do its cross product with the velocity, so what we get? We get a v sine theta. But what we want actually is a sine theta, right? So we need to eliminate this v, and for that we will just divide both sides with v. So v gets cancelled and this becomes a cross product v becomes a sine theta. This is also an important formula. So this kind of things is known as manipulation skills, okay, this kind of things, and it is often used in physics and mathematics. So also if we try to develop this kind of skills, we will be good at trigonometry, probability, and also calculus, specifically integration. So these are skills we have to develop, right? And now one important function, what it is doing is it is changing the direction, okay. Now if anytime we say that it becomes 0, what will happen? Let us imagine, suppose let's consider a case where this is block of mass m and moving with a velocity of v, okay. So in this case we can say that no direction is changing, it is moving in this direction, so no direction is changing, therefore this normal acceleration value is 0, okay. So when the normal acceleration value is 0, we see the velocity or the direction of velocity is same. So whenever this is equal to 0, the direction of velocity is constant, right? This is an important thing which we will use in the whole dynamics of circular motion. So it is a basic introduction, okay. So now let us start the dynamics portion. So before starting the dynamic motion, first let us visualize what does circular motion means. So whenever an object is moving in a circular path, it is said to be circular motion. So we'll try in circular motion dynamics portion, we'll try to understand that what are the causes that the object is moving in a circular track. So this is imagine this is the center of the circle and the object is moving in this direction, okay. So if we try to visualize this thing, we can say it that it is moving like this, right? It is moving like this. So as we know that the normal acceleration is responsible for changing the direction. So whenever the direction is being changed, there will be a normal acceleration which is acting towards the center. Okay, like you see, it is moving. So first it will have velocity v, like this, which will be a tangent at the point where we want to find. When it will come here, its velocity will be here. Okay, like this. And the normal acceleration will be downwards, because see, it is going downward, then again it is coming upward. So the normal acceleration decides its direction, and this is its velocity. Okay, and as we know, so first let us understand what is uniform circular motion. So in uniform circular, what happens? The velocity's magnitude is constant, but velocity is not constant. Remember this thing. If we remove these things, okay, let us just write the velocity. Okay. So this is the velocity. See, velocity is a vector quantity which can be defined as the magnitude of velocity and the direction of velocity. Okay, so it is a product of these two things. Now what we can say from this, that if the magnitude of velocity, that is speed, changes, the velocity will also change. Okay, and if the direction of velocity change, then the velocity will also change, or if both changes, then it will definitely change, right? So in this case, we can see that the direction of velocity was firstly here, then it goes here, then it again here, and it is here. So the direction of velocity at different point is constantly changing. It is changing, right? But magnitude is constant. So we can say as the velocity is changing, so we know that change of velocity, the rate of change of velocity gives us acceleration. Therefore this is an accelerated motion, right? This is an accelerated motion because the velocity is constantly changing, and whenever there is change in velocity, if we the rate of change of velocity gives us acceleration. So this is an accelerated motion where the magnitude of velocity is constant. Okay, so now if we want to find now let us talk about the tangential acceleration and the normal acceleration. So in this case, we will say that the tangential acceleration is equal to 0. Why tangential acceleration is equal to 0? Because the magnitude of velocity is constant. So as we have discussed earlier, if the magnitude of velocity is constant, then tangential acceleration is equal to 0. Because every time, at every point, the speed of the circular motion is same, right? Now let us talk about the normal acceleration. Okay, acceleration normal. So in this case, we'll see that as the direction is constantly changing, that in this point, see, after when the object is here, it is going upward, so something is pulling it upward, right? Some force or something. Whenever there is a force, there is an acceleration. So in this case, what acceleration is working? The acceleration is tangential acceleration. It is working towards the center. We have to remember that it always works towards the center, like this, which is responsible for the change in direction. And because of this because of this normal acceleration, it will be acceleration normal acceleration. Because of this normal acceleration, the direction of the motion is constantly changing. So the tangential acceleration is not equal to 0, right? It is changing, so it is not equal to 0. So we can also write that direction of velocity is changing. Okay, so direction of velocity is changing. Okay, so this is the basic part. Now let us learn what is angular moment, angular displacement, angular speed, and angular acceleration. Then we will again return to this part. So to start with, let us first learn what is angular displacement. We know what is displacement, right? But whenever an object is rotating around a circular path, if let this be the center, and if this is a position vector, let us call it as a radius vector, because okay, this is initial radius vector and this is final radius vector. It's radius vector final. So what we can say in this case, in this circular motion, better to say, the radius vector, let me show you. See, the radius vector is moving like this, right? It is moving like this. Okay, it is moving like this. So it is also having a certain displacement. So here what is the displacement? Here what is the displacement? That it has displaced a angle of theta. So here the theta is known as angular displacement. Also we can understand from the name itself, which says that angular displacement. So this theta is the angular displacement. Okay, this theta is the angular displacement. Next part which comes is the angular velocity. Okay, so angular displacement is represented by theta and angular velocity is represented by omega. Okay, so it's very simple, right? We have understood this angular displacement, so it is very easy for us to understand what is angular velocity. Angular velocity is nothing but the rate of change of angular displacement is the angular velocity. Like in kinematics, we used to say that if an object moves a displacement of x in a time t, okay, so what will be the velocity? What will be the average velocity? The average velocity becomes displacement by time, right? So similarly, here also we will do the same. Okay, we'll do the same, right? We'll do the same. So what is this angular velocity? Angular velocity is rate of change of displacement with respect to time. So we can write it that it is rate of change of displacement with respect to time, right? This can be its definition, but how we can calculate its value? So as we are saying that rate of change, so we'll differentiate this this angular displacement with respect to time will give us the angular velocity. The same as we did in kinematics. If we wanted in instantaneous velocity, what we did? We did dx by dt, which was also known as the velocity as the slope of xt graph. So similarly, here in this case, we are just differentiating angular displacement to get omega, which is angular velocity. Right? Same in kinematics we used to do, and here in circular motion we are doing the same. Okay. Now the last term here, which is angular acceleration. Okay, so now you have got an idea that rate of change of omega, which is rate of change of angular velocity, gives us this angular acceleration. Okay, so rate of change of angular velocity is the acceleration. Okay, it may happen that the velocity at this position, the velocity at this position is different, so then there will be angular acceleration. And okay, so you're understanding it, that rate of change of that velocity, angular velocity, will be acceleration. So it is denoted by the Greek symbol alpha. Again, we can differentiate omega with respect to time, will give us alpha, that is angular acceleration. As we did in kinematics, dv by dt is equal to a. Similarly, we are doing here. Okay, so now let us summarize this whole thing which we have studied here. So to summarize what we saw, that in kinematics, what is displacement? In circular motion, it is the theta. Okay, because it is rotating, so that is the theta. In kinematics, velocity and circular motion, that is omega, which is the angular velocity. So angular word is just added, rest all is same. You can see acceleration, angular acceleration. Okay, so if we want to get velocity from, if we want to get velocity from displacement, we used to differentiate. Again, if we want to get acceleration from velocity, we used to again differentiate, right? Like this, v a, differentiate. Okay, so if we want to get back to, again, if we have acceleration and if we want to get velocity, we used to integrate. And if we had velocity and we want to get displacement, we used to integrate. Similarly, in this case, if we have angular displacement, if we differentiate angular displacement, we will get omega, which is angular velocity. If we again differentiate it, will get alpha, which is angular acceleration. Now if we integrate, what will get? Will get omega, which is equal to integration of alpha dt. Okay, this will give omega. So if we integrate, we will get omega. And again, if we integrate, what will get? We will get theta is equal to integration of omega dt. Okay, we'll get like this, some results like this. So we can see that they are same, but they are still different from each other. One is happening on a circular track, another is happening on a straight or a plain straight line. Okay, one is happening on a straight line, another is on a circular track. So this is what the concept of angular displacement, angular velocity, and angular acceleration. Now let us again go back to uniform circular motion. So let's draw the circle again. Okay, now this is the center of the circle. Okay, the velocity at this point is here, at this point is here, and at this point is here. Okay, this point here is a tangent. It is a tangent line. So now, as we have described what is the angular, what is the angular displacement, what is angular velocity, what is angular acceleration. So first let us write those things which we had written previously. So, and also we will have a revision. Okay. So the velocity, magnitude of velocity is remaining constant, and if it is constant, at is equal to 0. But as normal acceleration is acting and which is causing the change in direction, so an is not equal to 0, which says that it is constantly changing, not constantly, it is changing, right? The normal acceleration or the centripetal acceleration is changing, right? Now let us describe that how can we calculate the, or how can we relate the angular displacement to angular velocity and angular. Okay, so first thing is that if we differentiate, we'll get omega. Okay, now if we take the second order derivative of this, we'll get alpha. This can be also written as d omega by dt is equal to alpha. So these are the basic formulas, but let us try to write in terms of all these things. Okay, so let us again imagine a situation. Also, as the normal acceleration is constantly changing, this is an accelerated motion. Accelerated motion, right? Again, let's draw the circle. This is the center, let's consider. So again, let us bring those manipulation skills. This is a vector. This is a vector which can be termed as the radius initial vector, and this is the final radius vector. Okay, and it will, and this is the angle which is displaced is very small, which can be written as d theta. Let's consider is d theta. So what is this displacement? This displacement is dx, and as we have studied in kinematics that dx by dt is equal to velocity. So if this length is of dx, then the value of dx will be dx is equal to vdt by cross multiplication, right? So just we'll simply put this value vdt. Now we have studied the formula in junior classes like 9th, 10th. Okay, so what is that formula? The formula is, if we want to find the angle is equal to the length of the arc length divided by radius. So let's consider that the radius of the circle is r. Okay, so the angle is d theta here. In this case, the angle is d theta. The length of the arc is dx, which is equal to v dt. So let's write it v dt. And the radius of the circle is r. Okay, the radius of the circle is r. So now if we shift this dt term here, so we'll get d theta by dt is equal to v by r. From this formula we can say that d theta by dt, which is differentiation of angular displacement with respect to time. So this gets us omega, which is equal to v by r. And therefore, if you want to find velocity is equal to r times omega. Clear? Velocity is equal to r times omega. So this is an important formula we have to take care of, right? This derivation is not important, but still I made it. So let us write this formula as a result. Okay, v is equal to r times omega. Now if we differentiate it, now let us differentiate, right? If we differentiate it, what we'll get? We'll get dv yes, dv by dt is equal to r into omega differentiation. Okay, so r is a constant, so it will be going out, so we have to differentiate d omega by dt, which gives us, so here v is not the velocity, here v is the magnitude of velocity, which is speed, and we have learned that the differentiation of speed with respect to time gives us the tangential acceleration, so which is equal to r into a differentiation of omega with respect to time gives us angular acceleration. So we can say that tangential acceleration is equal to r times omega. Okay, this is also an important result. Last but not the least, if we want to find the normal acceleration, so what will be the value of normal acceleration? So normal acceleration value comes out v square by r. Okay, v square by r. Now if we put the value of velocity, this, in the equation, so what we get? An is equal to r omega square whole square. So normal acceleration is equal to r omega square. So these are the basic formulas we have to take care of. Now if we write this equation, we know that the tangential acceleration in the case of uniform circular motion is equal to 0. So the value of r alpha must be equal to 0, where r is the radius of the circle and alpha is the angular acceleration. As r is the radius of circle, so it must have some value. Therefore r is a constant, and from this equation, as r has some value, we can say that angular acceleration is also equal to 0. So in circular motion, in uniform circular motion, angular acceleration is also equal to 0. So what are the things we have discussed? We have discussed that the magnitude of velocity, which is speed, remains constant. The tangential acceleration is equal to 0. The normal acceleration is not equal to 0 because the direction is changing. It is an accelerated motion because direction is changing, and velocity is multiplication of magnitude of velocity, that is speed, into direction of velocity. Okay, we are representing it by a unit vector, which is v cap. Okay, so we know that if this changes, the velocity will change, and if this changes, velocity will change, or if both changes, the velocity will change, and change in velocity will give us acceleration. So as this unit vector or the direction, we can say this direction, okay, not unit vector, direction is always changing in every part of the circular motion. The direction is changing. See, at this point here, at this point here, at this point here, at this point here, this point here, right? Direction is changing continuously. So as direction is changing, we can say that it is an accelerated motion. So for today, so thank you. I hope you liked my video. Thank you.